Okay, so I'm going to start a couple minutes early. I'm low on battery okay, so just to remind you where we left off before the test, I was talking about semaphores, and I introduced this notion of a semaphore, that it's an integer variable. You can do two operations on it, which decrements the semaphore and signal that increments the semaphore. I said when I decrement and if the value goes negative, the thread that calls the wait has to block. And when you signal, if there's a block thread, you're going to actually wake up on all those things. Okay? So those are the semantics, and then I showed you some code which I have put up here again on producers and consumers. And this was the first synchronization problem that we've encountered. I'm quickly going to go through this again, not the code but the concepts. So the basic idea is you have a shared buffer. Think of it as an array with n slots. Okay? Producers are threads that are producing data, okay, which they want to share or send to the consumers. Consumers consume the data, process it. Okay? And we use a shared buffer as a way to communicate. Okay? And the basic approach is the shared buffer is shared, obviously. So before you enter anything into the shared buffer or take something out of the shared buffer, you need to lock it. Okay? Because anything that is a shared data structure has to be locked prior to access. Okay? So we use a mutex semaphore, which is essentially a lock before you take something out of the buffer or put something into the shared buffer. Okay? So that's one thing. The other thing we need to do is to ensure correctness, and what that means is producers cannot produce any more data if the buffer is full. You assume that the array has n slots. Okay, this is a circular buffer. Keep that in mind. It's just basically circling through the buffer and just entering into the next available slot. But if all the slots are taken, or so the buffer is full, the producers have to block. Okay? And the same similar rule holds for the consumers. If the buffer is empty, there is nothing to consume. So consumers have to block until at least one producer produces the data. So we have to ensure both of these properties, and we'll see what we do is we have an empty semaphore and a full semaphore. Okay, so this full semaphore, you do a wait on this, and this says how full is the buffer. If it's completely empty, then this is going to cause the consumer to block. Okay? And the empty semaphore is basically saying, is there any more slots? And if there are none, then the producers. Okay? So that's the logic for semaphores. And you will see that it requires a little bit of thinking as to how to write all of this code. The code is not very easy or trivial to write. And we will see another way to write the same kind of code using monitors, which significantly simplifies all of this, makes it much easier to reason. So semaphores are a low-level construct for synchronization. Okay? And you can solve any problem you want with it, including producers and consumers, but writing code and reasoning about code is not the most straightforward task. Having said that, you're still expected to know how to write code using semaphores. Okay? And this would be an example of a problem you solve with semaphores. Okay? So that is just a recap of where we left off last time. There were lots of puzzled looks when I was talking about all of this. So I'm going to pause for a second and see if there are any questions on what the producer-consumer's problem is, okay, and the basic idea of how to solve it. Okay, and this code you might have to look at a couple of times, or if you have questions about this, I can answer. Okay, is this clear? What is a producers and consumers? We'll see other examples of how to solve it, which will make it much simpler as well. Okay, and I should say that this arises in a large number of contexts. Okay, so there are many synchronization problems that use producers and consumers. Simple example is when you play, let's say, a video, okay, whether it's a video player, YouTube or whatever, there's a buffer in your client. The consumer is the thread that is taking the data and actually displaying your video on the screen or sending the audio off to your speaker. Okay, and the producer is a thread that is actually receiving data from the network. Okay, data is arriving from a server somewhere. Running on the network, you put it into this buffer, the consumer thread takes it out of the buffer and decodes your video and displays it and so on. Just one of the many examples where you see these kinds of problems. Okay, so just to summarize, so I said that some semaphores are a generalization of blocks, and you can use the same construct in three different ways. Okay? There's good and bad. The good is it's flexible. The bad is you actually have to figure out when you see some semaphore in a code, which of these three things is it doing. Okay? The simplest thing is to use it as a binary semaphore, which is nothing but a lock. Okay? Also sometimes referred to as a mutex semaphore. You can use it as a counting semaphore where you initialize the semaphore to a value n rather than 1, in which case it can protect multiple instances of a resource. I gave an example of a bank of printers. N printers, they're all identical. Print jobs come in. You basically take the next available printer and assign the job to that printer. It doesn't really matter which printer is printing a job if they're all identical in this case and are all co-located. Okay? So that's an example of a counting semaphore. And the last but not least, we looked at how you can use a semaphore to enforce scheduling constraint, where you can have a thread block until some condition becomes true, okay, regardless of how the CPU scheduler schedules them. So you cause one thread to wait for a specific action to be signaled from another thread. And that is what we were doing in producers and consumers. Producers would signal a consumer saying, I just produced some data. If you're waiting, you are go ahead and consume it. And consumers can signal the producer saying, I consume some data, at least one more slot is available in the buffer, you need to produce something, produce it. So those are the kinds of constraints you can specify here. Okay? So that's basically a recap of semaphores. We'll just continue and talk about monitors, which is the third of our synchronization constructs. So I'll introduce monitors, but before that, we'll talk a little bit about some of these issues I was just describing with semaphores, which is what's wrong with them. Not technically wrong, just from a coding perspective, why is it harder to use them? Monitors will sort of try to address those issues. I'll describe what they are, how we implement them. We'll see producers and consumers redone with monitors. Okay? And then we'll have a comparison of semaphores and monitors. So we'll start with what is wrong with them. I think there are a number of issues here. So the main issue is they are a low-level construct, and there is no direct connection between a semaphore and a data item it is protecting, or a semaphore and a code that is actually being used in. Okay? They are like a variable. I said they're a special integer variable. So you can declare as many as you want. You can use them any way you want. In doing so, you can also have problems with your code. If your code is buggy, it might have race conditions and deadlocks and all sorts of problems. Okay? So there's no linguistic connection between the semaphore and the data which it accesses. You can put it and use semaphores anywhere in the program. And last but not least, the same construct is being used for three different things. Okay? It would have been better if you had actually three different constructs, each of which did one thing instead of overloading the use of semaphores, essentially. So we are using it to do mutual exclusion, either as a binary semaphore or counting semaphore, and using it to enforce scheduling constraints. So that complicates your code. Okay, just by looking at the use of a semaphore, you have to look at the code to figure out what it is being used for. Okay? And there is obviously no guarantee of proper usage. You can just write buggy code with semaphores. It's much harder to do with higher level constructs. So we want to implement synchronization at a slightly higher level of abstraction, which makes it easier to program. Okay, yes, question.
Yeah, I'm just wondering, when we use the word primitive to refer to these synchronization primitives, how are we defining that?
What is a primitive? Is that your question?
Well, what is a primitive in this case? Because it is a higher level.
Yes.
Like an object, basically.
Yes. So certainly you can do synchronization at a very low level. At the hardware level, you do enabling disabling interrupts.
And just given this reason that we're calling
a primitive. Yeah, I think it just means a construct. It's just a technical term. In this case, it's just used for abstraction. Okay? So locks are a synchronization primitive. Semaphores are a synchronization primitive. Monitors are a synchronization primitive.
So is it totally different usage of the word primitive than like the int versus a capital I integer, for example, in Java?
No, it's a sort of a similar use. It is just a different context in which we are using the word term primitive. Primitives are building blocks. Think of them that way, right? So depending on the context, in Java, primitives might be very low-level building blocks that relate to the programming language. Here we are talking about building blocks for doing synchronization. So we are using the same term in a different context. Okay, so just think building blocks if you use, or construct is another term that means essentially the same thing. Okay, so we need something at a higher level, and that's going to be a monitor. So let me describe what it is, and then we'll see how to use it. Okay, so monitors are essentially similar to a class, which probably all of you know if you're programmed in Java or C++. But it's a special kind of a class that ties together the data or the variables in the class, the methods of the class, and all the synchronization operations you want to perform on the data in the class. Okay, so it's a class like any other class, but it also allows you to perform synchronization. Okay, so that's basically what a monitor is. And unlike a traditional class or an object that is instantiated from that class, monitors, if you have a class that's a monitor, okay, or if you take a class and make it into a monitor, it is going to guarantee a mutual exclusion for you, okay, by just making it a monitor. So what does that mean? That means that only one thread can call any method of that class. Okay, if let's say you have a class foo and it has a method bar, or rather let's say object foo of a class and a method bar, if some thread calls foo.bar, okay, and it is executing bar, which is the method, another thread calls the same method, it will block, or any other method of that class. Okay, so only one thread can invoke any method. If some thread is executing a method, the class or the monitor will guarantee you that if other threads try to call method, they will block until the thread is done, and then you can continue. Okay, so it just look like it's taking longer for the method to execute because the thread is not even allowed to enter the method until some other method and the other thread has actually finished executing. Okay, that's the pause. That's really how the monitors are going to work. So the other thing that you have to use sort of follow in a monitor is all variables have to be private. Okay, and the reason for this is if you have public variables, you can modify them or access them without even calling a method. So that doesn't guarantee mutual exclusion or accessing data from the method. So if you make it private, you can only access the variables from methods that you call on the class, and the monitor is already guaranteeing you that only one thread can access the method, thus only one thread can access all the data for that class. Okay, so all data is supposed to be private and can only call one method at a time. Yes, question?
So if you have two instances of the same class that is a monitor, can you have threads doing those at the same time?
Yes, so question is if you have two instances of the same class, can threads call methods of these two different objects concurrently? And the answer is yes, you do this on a per object basis. Essentially, the monitor will have an internal lock for each object. Okay, two objects will have two different locks. Okay, all right. So here's a formal definition. Then I'm going to show you code, Java code, to show you how to do all of this. So essentially, a monitor, the way it works is it will define a lock and some additional things called condition variables. Okay, the lock is essentially internally declared. You no longer have to implement lock variable. So moment to make a class into a monitor, when you run it internally, all objects will have a lock associated with that monitor. And the lock is used to ensure that only one method of that object is called at any given time. Okay, if another method is invoked by some other thread, it won't get the lock. That's how it's going to block. Okay, that's the implementation of a monitor. Okay, this is how you ensure that threads are going to block. Okay, so the lock now also guarantees mutual exclusion of data that belongs to the object because we made all the variables private. Okay, you can only access them from methods. Only one method can execute. You are getting mutual exclusion automatically. Yeah, that means only one thread can access any variable of that object at any given time. So all data that belongs to the classes now become automatically you get mutual exclusion because of this lock. Okay, so all code is now critical section. All data is accessed in a mutually exclusive fashion. Okay, and what condition variables will do in addition to that lock? What condition variable will do, and we'll see why we need it. What they do is they enable the thread to go to sleep inside a method and release the lock. Okay, so if for any reason you want to block inside that method, Okay, you can essentially use a condition variable to go to sleep for some period of time and release the lock so some other thread can actually enter that method or some other method. Okay? So that's what a condition variable is, and we'll see in just a moment what it is used for in the context of a monitor. Okay, so here is what you can do. So monitors will encapsulate the data you want to protect. So it's inside an object, so it's a higher level construct. Okay, it will automatically get, whenever you call a method, a lock will get acquired, okay, by that thread. The thread doesn't have to do lock acquire. Thread simply calls a method bar, and in doing so, if it enters bar, it has a lock. Okay, that's what internally is happening when you use a monitor. Okay, it will operate on shared data, which are all private. So there's guaranteed, because it's holding the lock, it's guaranteed it's the only thread accessing that data. Okay, you can leave the mutex if you cannot continue using a condition variable. And the condition variables will also guarantee that when you wake up from sleep, you have the lock back. Okay? So you can temporarily give up the lock and go to sleep. When you wake up, the lock is given back to you. Okay? And then that lock that you have acquired in the method is automatically released when you exit the method. If you return from a method, the lock is given up. Okay? All this is happening inside a monitor. Okay? And we'll see you don't actually have to do much of this at all. You just write the class, you call it a monitor, and all this is happening for internally. Okay. And here is some code that just makes it more concrete. So I'm going to use Java as an example. And the reason is Java supports monitor out of the box. It's a language level support for monitors. Okay, and the good thing is it is very easy to turn any Java class you have ever written into a monitor. Okay. You just need to use one keyword, which is synchronized. Okay, and then if you use that keyword for a method, then that object has become a monitor. Okay? Here's an example. So this is a Java class. It has, so the other thing you have to ensure, of course, is all data for that class is private. Okay? So let's assume the data is private. We have a queue method. There's an add method for the queue and a remove method for the queue. Okay? So you just have a queue. Your threads adding and removing data items from this queue. The queue is a shared variable that's shared by threads. You want to ensure that you have mutual exclusion. If you're adding something to the queue, you don't want another thread to be removing something at the same time. Okay? And the way you're going to simply do this is you simply add the word synchronized in front of the add method and synchronized in front of the remove method. Okay? In doing so, this class has now become a monitor. Okay? And internally, Java will ensure that there's a lock associated with a queue object that you instantiate with this class. And whenever you call add, okay, because the method is synchronized, it will actually do internally a lock acquire. Okay? And then when you basically exit from this method, you will release the lock. Okay? So you'll see just a second. So you'll see that in the add, you're simply putting an item in the queue. In the remove, you just check if the queue is not empty and you remove the item. Yes, question.
So if Java's version, the queue data is supposed to be private, but if you forget and make it public, will Java alert you to that and say, look, this needs to be private, or is that just that would that be a bug?
Yeah. So if you have a monitor and you make public variables, by definition they are not protected because you can access them without calling a method. They're most different from a global like situation. So you don't get mutually exclusive access. Java is not going to alert you in that case, but you are not going to be guaranteed that that variable is accessed in a mutually exclusive way. Okay, so bad things happen if it's a shared variable. Yes, question.
Yes. So isn't it still going to be a problem with accessing the queue? Because add and remove are synchronized, but they're not synchronized against each other, right? So you're still dealing with one queue, and one thread could be adding at the same time what another thread is removing.
Okay, so the question is add and remove are both synchronized, but are they synchronized with respect to one another? Could you actually have add thread doing add while another thread is doing remove? That's your question, right? So there is a lock for the entire class or the object. Okay, just because these two methods are synchronized doesn't mean there's a lock for this method and the lock for this method. This simply tells Java that any method that is synchronized for that object, they all share one lock. Okay, and whenever you enter any synchronized method, then you have to get the lock. Internally, JVM will try to get a lock for the thread. Okay, so the reason you have to add the word synchronized is you might have additional non-public methods that you may not make synchronized. Okay, so you have to decide which, all your public methods have to be made synchronized. Okay, so and then they will all share one lock. It's not that there's one lock per method. Yes.
If you have two different private variables, let's say you have 4 methods, and 2 of them modify private variable A, and the other 2 modify private variable B. Can you make it so that the first 2 methods are synchronized with respect to each other, and the second are synchronized with respect to each other? So that
Okay. So question is, if you have independent methods that are accessing different private variables, can you get some concurrency by having separate forms of synchronization? That's your question, right? So in monitors, you have a global lock. Okay, you cannot get additional concurrency. There may be 3 methods here that don't have anything to do with one another. Some methods access some subset of them. There is no concurrency at that level. It's all or nothing, meaning that you basically have one global lock. If you have the lock, nothing else can happen. And that's the only thing that can happen. So that means if there are other variables, you cannot get that additional concurrency here. You can, of course, make it different classes or some other way that will allow you to get that concurrence. Because across objects of the class or across classes, you have different locks. Within a class, there's one lock per object. Okay. Any other questions here? Okay, so this is a very simple implementation of a monitor. Okay. You basically take any class, you add the word synchronized for any of the methods, turns into a monitor. Internally, when you call that method, a lock will be acquired for you. Okay, so now let us look at what you need. There's a question, yes.
Why, like, is there no example of a method that you could make unsynchronized and public?
Okay, is there any method that you could make unsynchronized and public? If you could, there is no requirement that it would not be, but you better be sure it's not accessing any shared variables, or if multiple threads enter that method at the same time, it's not going to cause any problems. If it shouldn't be a critical section. Okay, so standard better programming practice is that you make everything a critical section inside a monitor and have only the critical sections inside that monitor. Okay, but there's no requirement that you do that. Okay, so now we come to this notion of, I said a monitor is a lock and condition variables. I talked about the lock that comes to you when you say synchronized. Let's talk about condition variables and why you need them. So if you look at the code in the remove, okay, you check if the queue is not empty, you remove an item and you return the item. Okay, that's what the remove method is doing. Now, if the queue is empty, the remove method is not going to do anything. Okay, the thread will say remove something from the queue. You basically get nothing. When you have to realize that the queue is empty, you'll have to keep doing this until you actually get something out of the queue. Okay? Now, wouldn't it be nice if you call the remove method and if the queue is empty, the thread blocks until something is added to the queue. Okay? And only then does the method continue. It actually removes an item and succeeds. Okay? If you wanted your queue implementation to have those semantics, then you can use a condition variable. Okay? Now, if you go to sleep inside that method, realize that you are holding the lock because you made the method synchronized. So if you just blindly go to sleep saying, I'm going to simply wait until something adds something to some other thread adds something to the queue, that is never going to happen because the thread already holds the lock. Any other thread that calls add is going to block. Okay? So simply going to sleep inside a synchronized method doesn't let any other thread make progress. So what you want is not only to go to sleep, but also release the lock which you're holding because you have entered a synchronized method. Okay? And condition variables will allow you to do that. Okay? They will put the thread to sleep, okay? And they'll release the lock. So until the thread is woken up. Okay? So other threads can now enter synchronized method, do whatever they need to do. And when this thread that actually released the lock is woken up again, it is guaranteed to have the lock back, which you need because if you're in a synchronized method, you assume you have the lock. Okay? You yield the lock for some time, you wake up, if you're continuing execution, you better have the lock back because you're in the synchronized method. So all of this is again done for you by the condition variable. Okay? So you just use the condition variable to go to sleep, okay? And you yield the lock. You are now waiting, okay, and when you're woken up, you will basically have the lock back. So this is basically what condition variables are used for. So they enable a thread to sleep inside a critical section. The lock is atomically released, okay, when you go to sleep, and when you're woken up, you have the lock back. And now we look at the code again. Well, not yet. I'm going to tell you how to actually use condition variables first, then we'll look at the code again. So condition variables actually have, in most cases, two methods. Okay? In many cases, three. So they're like any other variable, but there are special ways to use these condition variables. So there is a wait method that puts the thread to sleep. Okay, so if you do a condition variable dot wait inside a synchronized method, the thread goes to sleep. It gives up the lock for that synchronized object, okay, and then some other thread will continue. Okay. A signal method will wake up a thread if it is asleep on that condition variable. So any number of threads can sleep on a condition variable. The way to wake up that thread is to explicitly send it a signal. So if you do condition variable dot signal inside any synchronized method, it will wake up one of the threads that is asleep on that condition variable, okay, which was basically here. Okay, if there's any thread waiting, a signal will wake up the thread. Okay, broadcast essentially wakes up all of the threads, not just one. Okay, if there are 10 threads, all of whom have actually done wait on a condition variable, broadcast will wake them all up. Okay, and then they will have to compete. Not all of them will progress. Okay? They'll all wake up. One of the threads will get scheduled first by the CPU. That's the thread that will actually get to make progress. Others will end up sleeping again, okay, as we will see. And there was a question here somewhere. Okay, so again, you use condition variable to put a thread to sleep, and there's a wait method that actually puts it to sleep, and signal wakes it up. So let's look at some code for the queue that will do this. The same concepts apply in Java. Again, Java supports condition variables as part of its monitor implementation. The only difference is wait is the same thing. Rather than calling the method signal, in the Java world it's called notify. And rather than using broadcast in the Java world, it's called notify all. Okay, so in the code, you won't actually write signal for Java. In C, if you use condition variables, you will actually use signal. Okay, they mean the same thing. The name of the methods is different across languages and or libraries. Okay, so in the Java world, this is what we are going to do. Okay, this is our add method. Same as before, it's synchronized. You put the item on the queue and you just call a notify. Okay, what notify does is if there is a sleeping thread, it will wake it up. If there's no sleeping thread, it doesn't do anything. There's no one to notify in this case. Okay? So you always say, I just put an item on the queue. If some thread was asleep waiting for an item to appear on the queue, wake it up. So you just put a notify there. Okay? And here is our synchronized method remove. Okay? And here what you are going to now do is you are going to have a while loop saying while the queue is empty, wait. So you are inside a synchronized method. You say, is the queue empty? Okay? Yes, go to sleep. Okay? Then you go to sleep, you give up the lock, which allows a subsequent thread to enter the add method. Other threads may also enter the remove methods. They'll also do this check, excuse me, and go to sleep. Okay? Any number of threads can be sleeping on the wait. Okay? This notify is actually going to wake up one of these threads that are asleep. Okay? And then once you wake up, you have the lock back, you will check again, is the queue still empty? You have to do that because you can have a race condition. Okay? You might, after a thread has added an item, there are threads sleeping, waiting for items to appear, but a new thread might appear, it might enter, remove and take that item out. Okay? Before the sleeping thread has woken up and gotten scheduled. So you cannot assume that just because you got woken up as a result of notify, the condition is now true. Okay, it might take some time for you to actually run on the CPU. Some other thread may have come along, called remove, and already consume that item, and the queue may again become empty. So it's always put a while. Okay, you wake up from a notify, check that the condition is still true, okay, which is the queue is not empty. If some other thread has come and done something and made it empty again, go back to sleep. That's what this code is doing. Okay, there are two questions there. No? Okay. Yes. Bye.
So does the notify method automatically give the lock to the sleeping method?
Okay. Question is the notify method automatically give the lock? That's your question, right? We look at two different implementations of monitors. One in which the lock is explicitly transferred to a thread that is woken up. Another one in which threads are woken up, they compete for the lock, and one of them actually gets the lock. Okay, so that is an implementation detail of how the lock gets transferred. Okay. In the Java world, the answer to your question in Java world, until you exit the method, all that notify has done is woken up a thread. You are still in a synchronized method, so you haven't internally done a lock.release. When you exit this method, Java will automatically call lock.release, at which point this thread will actually do something. Okay, we'll actually get the lock. Any other questions? Okay, so this is the queue method. We'll see how to do producers and consumers as well, but it's not very different from this. Okay? So as you can see, now you are writing code at a much higher level of abstraction. You are no longer explicitly getting locks, releasing locks. Okay, you're using condition variables to do certain things like going to sleep and things like that, but you're not writing low-level code. Okay? So this code is much easier to write and much easier to understand. If you had written the same exact code using semaphores, there'll be a lot more semaphores. Some will be mutexes. Some will be the equivalent of what you're doing for condition variables. You're using them for scheduling constraints. So much harder to write the same code. Okay. So now monitors are allowing you to program at a higher level of abstraction. Okay. You can solve the same problem, but now it's easier to write, understand, modify, and so on. Okay. So let us now talk about the question that was actually asked, which is what happens when you call notify or signal? What happens to the lock? How does it get transferred to the thread that has now been woken up? Okay. Now, if you look at various implementations of monitors, you'll see that they fall into two categories, and rather than calling it category 1 and category 2, they actually have names associated with them. One category is called a Mesa-style monitor implementation. The other is called Hoare-style monitor implementation. The names have to do with the first time these monitors are used in this fashion in those systems or in some papers. So the main difference between the two is as follows. In a Mesa-style implementation, okay, what happens is what I just talked about in the previous slide. When you call a signal, you wake up a thread, but if you're in the synchronized method, you hold the lock. You're not just giving up the lock just because you woke up a thread. Once you exit the method, you will give up the lock. Okay? So in other words, the thread that signals keeps the lock, and the processor and the waiting thread has to wait for the lock to be given up. Okay? That's what I showed you on the previous slide. That's what happens in the Java case. That's what happens in many other systems, real operating systems. Use these semantics for monitors. Okay. There's another semantics that's now not used in real systems anymore. A long time ago they were. So at this point, this is only in textbooks, but it's nevertheless instructive to understand what it does. So in this case, if you use the Hoare-style monitors, the thread that called the signal is going to explicitly transfer its lock to a waiting thread. Okay? You not only wake up the thread, but you say, here is the lock, and you actually transfer the lock. You don't wait until the CPU scheduler has scheduled it, and then you sort of compete for the lock and so on. There's an explicit transfer. Okay? So in this case, I will see that actually simplifies a few things when you write code. Okay? So in this case, when the thread was waiting, it starts executing, it already has the lock, and because it got transferred. Okay? So there are these two methods. Okay? They are implementation detail. At a higher level, they are both monitor implementations. Yes, question.
What happens in the horse? I don't know if I'm pronouncing this right. In the second style, what happens to if say you call broadcast, what happens to the other waiting threads? Because it seems to exchange simply between the thread that got the lock and then the thread that did the signal. But like now the thread that did the signal is no longer done the signal, and it's been broadcast.
So if you call broadcast in this case, there's not any difference between the two scenarios. Because broadcast is waiting all the threads. You can't give the lock to all the threads. That doesn't make any sense. So in that case, for broadcast, there is no difference. The only difference in semantics is for signal. Okay? And by and large, signal is the more common thing to do. Broadcast is supported by some languages, including Java, which is notify all, but not all monitor implementations will have the broadcast method. They will all have the wait and signal for sure. But the broadcast is an additional thing that some implementations now support. Okay, and then if you have broadcast and over, there's no different. You will wake up all the threads. So now, if you want to now go back and rewrite that Java Q code using Hoare-style monitors, what changes? You can say, okay, now I understand there are these two implementations. How does it matter from coding perspective? Does it change anything in how you, the programmer, approaches your code? Okay. And there's only one subtle change. Nothing much changes at all. Here is your Q class. It's a synchronized, or some monitors we have synchronized add. Add doesn't change at all. Okay, you just add the item, you put notify. Okay, and remove is also synchronized, but there's only one difference. Okay, the while statement becomes an if statement. Okay, now the reason this is the case is in Hoare-style, you are guaranteed that when you call a notify, it explicitly transfers a lock to a thread that is asleep on a condition variable. So if you are woken up from your wait, okay, you know that the lock directly came from the thread that called notify to you. Okay, and if that thread has actually just put a data item on the queue, you are guaranteed that the queue is still not empty. Then nothing else could have happened in the meantime. Okay? Because the lock is transferred explicitly from thread A to thread B. Even if other threads try to run in the meanwhile, okay, they will all block on the synchronize because they won't have the lock. The lock went from one thread to another. It's like you just explicitly hand the lock to another thread. So you are guaranteed that this condition on which you are asleep has changed. Okay, it's not still going to stay true. Okay, or in this case, it's false because you are woken up because the queue is no longer empty. So you don't need to check again. Okay? In the Mesa style, when your call notify is called, the thread is just woken up. It hasn't been given the lock. It has to compete for the lock. Some other threads may run. They may call a synchronized method, either these or some other, and grab the lock. They may make the condition go back to false. So anything can happen. As a result, you have to write a while to check that the condition is still true when you actually execute on the processor. Okay? That's the only difference. Okay? So if you had Mesa style, you could simplify your condition variable code. Instead of a while check, you do an if check. That's about the only difference from a coding perspective. Okay? Any questions here? All right. So now that we know what monitors are, how to use them in the Java world, what condition variables are, let me talk a little bit about how this works in C++, and then we'll go back to doing producers and consumers using monitors. Okay, and we'll see how they're different. So in the C and C++ world, it's not as straightforward. It's not supported at the language level. You have to use a library. Typically, you will use a pthreads library that will use monitors and whatnot. Okay? So there's no direct support, no synchronization keyword. So you have to explicitly declare the lock and release it and so on. Okay? So here is the same queue implementation. Okay? Now, this is all pseudocode, but I assume this is C++ code now, no longer Java code. Okay? So we have the class, Q class. It has two public methods, add and remove. Okay? Internally, you're going to actually have to declare a lock because you don't have the synchronized keyword, unlike in Java, which does it for you. Okay? You declare the lock. Okay? And then what you now do is in your monitor class, you always put a lock acquire at the beginning of the method and a lock release at the end. That's equivalent to putting the keyword synchronized in Java. And then if you do that, Java does these two statements for you internally. In C++, you have to make it explicit. So you will see that the first statement of the add method is an acquire on the lock and the last statement is a release. The same is true here. So every synchronized method in Java in the C++ world would have a lock acquire at the beginning and a lock release at the exit. Okay, so now you are writing all this extra code, but it's still the same concept. Okay? And you also have the data. So you do have condition variables, okay, which do the same thing. okay, as you are doing Java. So essentially you will do lock acquire, you put an item on the queue, you will do a signal on the condition variable, says if some thread is asleep, okay, wake it up, okay, and then you release the lock. Right? Here you will do a lock acquire, you will do the same while check while the queue is empty, go to sleep on the condition variable, you explicitly specify which lock you are releasing on this condition variable, that's an argument in this case, saying this is the lock to release when you go to sleep, that is the lock you are going to pass as an argument there. So you go to sleep, that signal will wake you up eventually. Okay, and then you check the while loop again, the while condition, and then it's still not true. You come here, take an item out of the queue, okay, and then you release it. Okay, so this is the equivalent pseudocode. Okay? And this code will not work. You actually have to use the pthreads library, which will have specific names for all of these things. Okay, but this is the equivalent pseudocode version of your queue implementation in C++. Okay, so you have to make things look like a monitor. In Java, it comes for free because the synchronize keyword will do all of that for you. Okay, any questions here? All right. Yes, question.
Are condition variables pretty much the same as semaphores?
Okay, good question. Yes, condition variables same as semaphores. So I have 3 slides coming up that will talk about are they the same or not. They have wait and signal. Okay, semaphores have wait and signal. So that's a natural question to ask. Are they the same thing? Okay, the answer is no, but I'll tell you why in a little bit. Okay, so here is bounded buffer using Hoare-style semantics. Okay, now again C++ pseudocode, we are going to do our producer-consumer bounded buffer problem. Okay, which means producers are threads that produce data item. There's an array of size n, okay, which is our shared buffer. Consumers consume from the consume data from the shared buffer. Okay, so we are going to use monitors to do this, but not in Java. Java things wouldn't have the lock acquire and lock release. So essentially what you need to do is we'll use 2 condition variables here. Okay? Producers are going to sleep if the buffer is full. Consumers are going to sleep if the buffer is empty. Okay? So we'll use 2 condition variables. Producers will use a condition variable that says if the buffer is full, go to sleep, release the lock, let consumers run. Consumers will use a second, different condition variable. It's the first time we are going to encounter a scenario where we have 2 condition variables. Then needless to say, you can have as many as you want. Okay, whatever condition you are trying to check, you have a condition variable for that condition. That's why it's called a condition variable. Okay, here we will have 2. Okay, the 2 condition variables are going to be called empty and full. Okay, there are 2 condition variables. One that checks whether nothing is full and the one that checks whether it's empty. So if you look at the code there, you say if the count equal to n, that means there are n items in the buffer is full. Okay, that's an array of size n. So the buffer is full, put the producer to sleep. So you will do an empty.wait. Okay, wait until at least one slot becomes empty. Okay, so you basically give up the lock and go to sleep. Okay, and if that's not the case, you'll produce an item and you'll put it in the buffer. Okay, you put say last is you put the item and then increment the pointer saying where is the next item going to be added. Okay, so that's basically the producer. And then once you've done that, you do a full dot signal which says if a consumer is asleep, okay, if waiting for a data item, this thread just produced one. So you signal a consumer. So you do a signal of a different condition variable. That was an empty.wait up there. Here you do a full dot signal. Okay? So you are basically playing around with 2 condition variables, signaling threads. Okay? The consumer will do the opposite. You will always do a lock acquire and a lock release. That's your monitor. Here you check is count equal to 0. Is the buffer empty? The buffer is empty. There is nothing to consume. Okay? Put the thread to sleep. So you are going to do a full dot wait. Okay? So you give up the thread, give up the lock, not the thread, and you go to sleep. Okay? And then here is where you will get woken up. If a producer runs subsequently, at the end it will do full dot signal that will wake up the thread. Okay? And because it's Hoare-style, these are if statements. Okay? If you are doing Mesa style, if this was Java, you would have done a while count equal to 0 and while count equal to n. But here this is Hoare-style, so we just use an if statement. Okay, so if the buffer is empty, go to sleep. If not, take an item from the buffer, decrement, okay, and then wake up a producer if one is asleep. Okay, if you basically were asleep on count equal to n, there this is where a consumer would wake you up by signaling. Okay, two condition variables, one shared buffer, and you're checking whether the buffer is full. You got new producer sleep. If the buffer is empty, consumer sleep. Okay, so this is now the same code that I showed at the beginning of the class from last time, implemented using monitors. Okay. If you had Java, then all you would have done is made this method synchronize, made that method synchronize, these log statements would go away. Okay, that's automatic, but the condition variables you still implement. You would need two condition variables, one to check whether the buffer is full, one to check whether it's empty. Any questions on this? Anything that I can explain again before we move on to other things? Is this clear by and large? I think this is probably, we'll see it, maybe see this one more time later. But let's come back to the question that was asked, which was, are condition variables the same as semaphores? They have wait and signal method. This seems very similar to a semaphore's wait and signal method. Are they one and the same thing? Okay? In other words, if you actually had a semaphore implementation, okay, could you write a wrapper code which says the condition variable wait essentially calls a semaphore wait internally, and a condition variable signal calls a semaphore signal internally. Okay, could you implement a condition variable internally using a semaphore? Okay, which basically just takes a wait on this condition variable and calls a wait on the internal semaphore, and it's the same for a signal. Will that work or not work? Okay, that's the question, and then we'll have a discussion of what that means. Is that clear why we are even asking this question? They seem to have the same name method. Is there a reason or not? Okay. So the answer, as I was hinting earlier, is they are actually not the same things. Okay. There's a certain difference between the two. They look similar, okay, but they are not the same. Okay. If you do actually do that condition variable dot wait and signal, you will not get the same results. Okay. And the reason for this is the following. The semantics of semaphore wait depends on the value of the semaphore. Okay, so if you remember, if you do from 2 classes ago, maybe more than 2 because there's a test somewhere in between. If you remember, what does semaphore.wait do? Okay, I said semaphore.wait always decrements the semaphore first. Okay? Then you check the value of the semaphore. If the value has gone negative, then the thread blocks. Okay? Remember, so that's what we said. So if you want to use it as a lock, you basically initialize semaphore to 1. Okay, that's a binary semaphore. You initialize it to 1. The first thread that calls wait is going to decrement it. Okay? Value will go to 0. Okay? It's not negative. So wait is simply going to continue. It's like acquiring a lock. You acquire the lock, you don't block on the acquire. This is the first thread and you just enter your critical section. This has done the same thing. Okay? So what happens in wait actually depends on the value of the semaphore. Now if a second thread calls a semaphore while the first thread is still in wait, the value is going to go from 0, it will get decremented again, it will go negative. Okay? And I said now you block. Okay? Because when the value is negative, you are going to block. Okay? So those are the semantics of semaphore wait. I'm just doing a recap so you understand why condition variable wait is not the same as a semaphore wait. Okay. Now let's look at this code that we had here. Okay. So you do a condition variable wait. What's happening in this case? Okay. You give up the lock, that part is fine, that's not the same here. But you always go to sleep. Okay. When you call up wait on a condition variable, you're always going to go to sleep. The thread is going to go to sleep and it is going to release the lock. Okay? That's not the case in the case of semaphore. In semaphore, whether you block inside a wait or not depends on the value of the semaphore. In a condition variable, there is no such concept. If you call wait, you are always going to sleep. Okay, so they are not one and the same thing. Okay, in one case, you are actually looking at the value of the variable, the integer variable associated with the semaphore, and then deciding should the thread continue or should it block inside wait. In here, you are always going to block. Okay. As a result, you will see that they are not the same thing. If you had blindly used a semaphore for a condition variable, what might have happened is based on how you I should be going forward, not back. So what may have happened here is if the queue was empty and you called wait and you initialize the condition variable to 1, it will simply go to 0 and you won't even block. Okay, you will simply continue because the value has not gone negatively. Okay, that's a problem. Okay. So that's one reason why they are not the same. Okay, you can do an analysis of semaphore signal and condition wait signal and see other differences as well. Okay, so you have. Okay, and let me explain how they are different from the implementation of the signal method. I talked about how they are different from the perspective of the wait methods. Okay. In the signal method, what condition variable dot signal says is that if there is a thread asleep. Okay, so if you go back to the Java to here. Okay. So signal is same as notify. Okay, so what notify does is what the meaning of notify is that if there is a thread that is asleep, wake it up. Okay. Otherwise, do nothing. That's what it means. Okay, so if it says you put a data item into the queue, okay, if there is a sleeping thread, wake it up. If there is none, then there is nothing to do. You just basically, the notify method doesn't do anything. Okay. That is the same as cv.signal and cv.notify are one and the same. Okay. In this case, okay, if semaphore.signal says increment the semaphore. Okay, so you actually incremented it. Okay, and then you are going to say is the value still less than or equal to 0, then wake up a thread. Okay? So you are going to actually do different things. So even if there is no thread, okay, in this case you are incrementing the semaphore. That impacts any subsequent wait because it will decrement it again. Okay, in this case, signal will not do anything if there is no waiting thread. Okay, in this case, signal will actually increment the value of the semaphore, which means that any subsequent wait will go back and decrement it and perhaps not blocked as a result of the increment. Okay, so they do different things. Okay, the methods are the same. That is a bit unfortunate, the choice of the names of the methods, but that does not mean that they are one and the same. Semaphores and condition variables do very different things, even though the wait and the signal methods are the same, have the same names for both of them. Okay, so I think here is some more information on what I just said. Condition variable do not have any history and semaphores do. Okay, what that means is semaphore has a value associated with it. So it's an integer variable. You explicitly increment and decrement value. So it has a state. Okay, the state is the value of the semaphore. Okay. Condition variables don't have any state. They just simply mean wait just means block. Okay. There is no ifs and buts. You always block. Signal just says if something is asleep, wake it up. Okay. There's nothing more that you do there. In semaphores, because you have a value and what wait and signal do depends on the current value of the semaphores, they actually end up doing very different things. Okay. We use that before. Okay. So that's the essential difference between the two. There are other ways to look at the same thing, what I said. In semaphore, wait and signal are commutative. Okay. They do the same thing regardless of the order. In condition variables, they are not. Okay. So let's see what that means. Okay. So let's say you have some code where you start with semaphore equal to, let's make that 0 just to make it interesting. Okay, first. So you have semaphore values initialized to 0. First, some thread, one thread calls wait. Okay? That makes the value go negative. Okay? So this essentially will block. Okay? Subsequently, another thread called signal. Okay, that will increment the value again. It will go back to 0. You will unblock. Okay, that's what will happen. If you initialize the semaphore to 0, if the first thread calls a wait, it will block. Second thread calls a signal, it will unblock it. This looks the same as condition variables, where if you do cv.wait, you block. And you do cv.signal, you unblock that thread. Okay. In this case, they are doing the same thing. And now let's do something different. Let us actually change the order. Okay, so we switch the order. The thread, first thread calls the signal of the semaphore, and then you call a wait. Okay, so what happens when you call a signal?
Increment.
Will increment. Signal should always say increment. So this will cause the value to go to 1. Okay, so there's nothing more that happens here. Then another thread calls the wait. Okay, wait will decrement it again from 1 back to 0. You check, is the value negative? It's not, it's only 0, so there is no blocking here. Okay, because you called a signal, it incremented. So initially you started with 0, you call signal, this made the value go to 1, then you call a wait, that decrements the value back to 0, it's not negative. So this thread will not block if that is the order in which things happen. Okay, now we'll do the same thing here. You do signal, okay, and you do wait. Okay. So when you do condition variable dot signal, you say, is there a thread asleep? If so, wake it up. Okay. So in this case, this is the first thread that's running. There's nothing asleep at this point. So signal will have no impact at all. It will just execute and say there's nothing blocked, so there's nothing to wake up. Okay, so that's what signal will do. And then the second thread comes along and calls condition variable dot wait, okay, which, as I said, you always block. Right? I said when you call a wait, you give up the lock and you block. Okay, so now you are blocked. So you will see now they have done two different things here. Okay? In this case, the wait, a signal followed by a wait, did not cause a thread to block in the case of a semaphore. In case of a condition variable, a signal followed by wait will always, the wait always blocks. It doesn't matter what has come before it. Okay, so now I showed two examples. One in which case the semaphore, the wait comes before the signal, and the semaphore does exactly the same as this condition variable. And I showed you another example when you flip the statements. The semaphore behaves differently from a condition variable. So this should give you a very concrete scenario that tells you that two don't do the same thing. Okay? That's also meant by this commutative thing. Saying the result is sort of the same because you're tracking the weight and the signal through the value of the integer. Okay? In this case, it's not the same. Weight will always block. The weight doesn't depend on what has come before it. Okay? There's nothing, no state you're tracking. Okay? So having said that, you could still ask the question, if you are given semaphores, could you implement condition variables and monitors and so on? Okay, the answer is still yes, but it's not the same as taking a weight and wrapping it with a condition variable weight and signal with a condition variable signal. That doesn't work. The implementation of monitors using semaphores is a lot more complicated. That's what is shown here. Okay, that's actually a 2-slide set of code. So we will basically look at it quickly and then move on to other things. Okay, so now what our goal is to implement the notion of condition variables given semaphores. Okay, so you are given semaphores. You are said implement a condition variable library that other people can use. Okay, that actually implements the condition variable semantics. How would you do that? Okay, so this is what you need to do. You are going to actually have in your implementation of the library 3 different semaphores. Okay? One is actually going to be a lock. Okay? You're not just, so that's basically the lock for the monitor. Okay? That's a mutex semaphore. Okay? And then there is a condition variable semaphore which is going to implement condition variable. There's a next semaphores as well, okay, which we'll see how to use. And you have an integer that counts how many threads are asleep, okay, on that condition variable. Okay, just keeping track of if a thread sleeps, you just increment that. Okay. So this is your constructor for the class, monitor class. So condition variable is basically set to 0. That's that semaphore here. Okay, initialize the semaphore to 0. Lock is free. Okay, lock is another semaphore. It's a binary semaphore, so you set it to 1. Okay, and you set the number of waiting threads and next count all of that to 0. Okay, and this is essentially the code for condition wait and condition signal. Okay, that's one method there, one method here. Okay, so when you enter condition variable wait, okay, you are going to increment the number of waiters. Okay, this is basically saying one more thread waiting. If you say if the next count is greater than 0, you resume a suspended thread. Okay, otherwise, you will allow a thread to go into the monitor. Okay, so essentially, and then you will do a wait on the condition variable, and I'll explain some of this in just a moment. Okay. And in the signal, you see is the number of waiters is greater than 0, you do nothing. Okay. It says that no thread is waiting, don't do anything. Otherwise, what you're going to do is you're essentially going to have to wake up a waiting thread. Okay. And that is what all of that does. You say next count 1, you'll do a signal on the condition variable, that's a signal on the semaphore, and you will do a next dot wait, which is going to essentially do another wait, and you will decrement the count. Okay, yes, there's a question there.
Just put a fire point on what the next count is.
Okay, so question is, what is the next count doing? So in this case, let me go back here and say, essentially it's the number of suspended threads on next. Okay, that's it. So it's basically saying this is a semaphore that suspends the thread when signaling another thread. Okay? And then this is how many threads are asleep on that next count. Okay, so the implementation is a lot more complicated than just having one semaphore to do the whole thing. So you have a thread that is suspended on a wait, and then additional threads that are essentially getting suspended when you signal one another. This is counting how many of those are in there. Okay, that's an integer variable. Okay, there's a question in the back. Yes.
Is this Hobble's monitors included by building the semaphores, or are there other ways to do it?
Okay, question. That's another good question. The question is this how monitors are implemented? Okay, so the answer is that depends. Okay, there are many ways to implement monitors. You can just go directly to low-level constructs, which are test set instructions. You can use interrupts and directly implement them that way. Okay? Another way to implement them is you're given another synchronization primitive such as a lock or a semaphore, and you can implement monitor. So what I will say is the following. Okay, from an expressive power standpoint, semaphores, locks, and monitors are all equally powerful in that any synchronization problem that you've been given can be solved by any of these 3 methods. The amount of code you may write to solve it will be vastly different because you're programming at different levels of abstraction. So all of them are equivalent from an expressive power standpoint. What that also means is that if you're given one of them, okay, you can implement a library for the other 2. Okay, so you could say, I'm given a semaphore, implement a library for a monitor. I'm given a semaphore, implement a lock. That's very trivial. You just make it a binary semaphore. Okay? Or you could be given a lock and say, now you have given a lock, go implement everything else. Okay? That's also possible. Okay? You can also take a monitor and make a lock out of it, which sort of is given for you if you just use synchronize and so on. Okay? So this is just an exercise to show you, having argued that they are not one and the same, you can still implement a condition variable and a monitor class using semaphores. Okay? The takeaway is not that trivial. You have to do lots of things internally in terms of tracking threads when they call a signal and a wait and doing the appropriate thing so you get the same semantics of what you want. Okay? So it's a lot more complicated from that perspective. Is that clear? Any other question here on the... So I don't know whether I should go into every line of that code and explain it or just leave it at that, just to give you the an idea that yes, it can be done and it's not straightforward. That's really what I wanted to convey. But we could certainly look at the code as well. Okay, so that is where we are with respect to monitor. So we have looked at 3 different constructs by this point in time. Okay, you've done locks, you've done semaphores, and you have done monitors. Okay? From a Java perspective, monitors come out of the box. Okay, so using the word synchronized and using condition variable is all given to you. Okay, you can also have libraries for locks if you just wanted to use locks separately from monitors and so on. Okay. If you are writing code in C or C++ Word, most likely you are going to be using the pthreads library, the POSIX threads library, which not only implements threading, it also implements synchronization for your threads. Okay. So you will see that it will support a mutex, it will support the notion of a semaphore, it will even support a condition variable, but it does not give you a full-blown implementation of monitors. Okay, you will have to actually put a lock acquire and a lock release at the beginning and the end of your synchronized methods. Okay, so it is a much lower level, but you get some of these abstractions. Okay. Your next lab will require you to use one of these synchronization methods and threading. So it's good for you to then go and look at how to write real code using some of these synchronization methods. Okay. So let me just continue from that point on. I just want to introduce in the next 10 minutes our next synchronization problem, which is called the reader-writer problem. Okay. This is going to help us. So we looked at producers and consumers. Okay. And I already mentioned that this is a class of synchronization problem that has much broader use. There are many real problems where it boils down to producer-consumer scenario. You use the template code that I showed you. Now I'm going to show you another synchronization problem called readers and writers that also has broad applicability. Yeah, then we'll see a third one called dining philosophers, but not today. We'll look at that tomorrow when I do the class during the discussion section. So here is the reader-writer problem. Yeah, and then we'll see why the 3 things we have looked at so far are not adequate, right? Or there are better ways to do it. So the reader-writer problem is as follows. So let's assume there's a shared data structure. Let's say it's a shared integer. It doesn't matter what the shared data item is. And you have threads that are accessing and reading the value of that data item, and other threads that are modifying the value of the data item. Okay. So there are some threads that are reading the shared variable, other threads are writing or modifying the shared variable. Okay. Now because this variable is shared, you have to protect it inside a critical section. Okay. We said anything that is shared is accessed by multiple threads, protect. Okay. That's a standard procedure. So the standard way to solve this problem is that both readers and writers will use a lock to protect your data. So before you read or before you write, you're essentially going to use a lock. Okay? So you might have a read method, you might have a write method. You can use a lock, then you read the data item. In the write method, you get a lock and you modify the data item. That's one way to solve the synchronization problem, and that's a fine way to solve the synchronization problem. But then you can ask the question, can we actually do better in terms of getting more concurrency? Because this you're protecting the data item by lock, it is a given that only one thread can read or write to this variable at any given time. There's always a lock. Okay? So now what happens if I had 100 readers and 1 writer? Okay, let's say you have lots of reading threads, only 1 writing thread. Do you need to use the same lock to protect the data item if there are more reads than writes? Okay? Or put another way, if one thread is actually reading the data item, okay, can you let another thread read at the same time, concurrently? Is that a bad thing, or should you still protect the data item by lock and only have one reader? Yes?
If they're both reading, it might not be a problem, but if one's reading and one's writing, then that's the
Okay, so what is just being mentioned is if both threads are reading, it's not a problem. They're not modifying the data item. Both will read the same value. Okay? But if any thread is writing, then no one else should be allowed to read. Okay? Because if you're modifying it, you read at the same time, that's a problem. And that you don't want to let happen. Okay, but it's perfectly fine to let multiple readers read at the same time, so they're not modifying. Okay. So can you then use this insight to get more concurrency? Okay. Which means that if there are multiple readers in your system, let them read concurrently. In this case, you do not want the lock to hold back other readers. Okay? The lock that you used will always block any other reader or writer by default. Okay, but can we then get more concurrency by saying if you are accessing the data item in read mode, I'm not going to modify it, let as many readers read as you want. But now if you want to modify, then everything else should be blocked. The writer should block all other threads, whether they're reading or writing, while you're writing. A reader should not block any other readers. Okay, but then the writer has to wait until the reader is done before it modifies. So question.
So, so you just said that the writer will always wait until all the readers are done? So, because I'm like looking at that problem, you can't have the writer, in all previous works, we were having it that the thread that's about to hit the critical section is the one that blocks itself.
Yes.
So it's not possible for the writer to send out like a reverse broadcast telling all the readers to block themselves.
So we are talking about how to implement a solution to this problem. We will see many different implementation. Some of them will have problems. Others may do something along the lines of what you said. I was simply trying to motivate the problem, saying that if you have a shared data structure where there are reading threads and writing threads, then rather than simply protecting it by a coarse grain lock that blocks all other threads when any thread is reading or writing, you may be able to get more concurrency by allowing multiple concurrent readers, okay, to access the data at the same time. But if there's any writer, then everything else gets blocked when the writer is writing. Okay. This will allow you to have more concurrency in your system. The simple lock still gives you correctness. There is no problem with the solution there. You will always have a correct solution, but you are getting less concurrency than you want. Okay? And you might say, who cares about such things? This is even an important problem to solve. Okay? So I will claim that this is a very important problem in many scenarios. Okay? Good scenarios, example is a database. Okay? Think of a database. Okay? So database, if you heard of what a database is or know what it is, there are tables that have data in the database. You might actually send queries that are simply reading from the database. Okay? You might say, go and look up the grade for this student. Okay? Go and do some other thing in this. Okay? So now if you protected the database or your table with a lock, okay, then only one of these threads can actually do anything on that database. Okay? Think about Spire. Okay? You are trying to register. You say, is there a seat available? Okay? That's simply a read operation. Okay? You just say how many seats are taken in the class. Okay? Now if you have to wait because 20 other students are actually trying to access how many seats are taken, then you will actually, your query is going to take a long time and you will feel that Spire is very slow. Okay? But on the other hand, since you're only asking how many seats are available, if no one is actually trying to register for that class at that point, which is a writer, okay? Why not let anyone who wants to see how many seats are available all read that seat count all at once? That would be fine. No harm done. Okay? So these kinds of problems become very important in databases where there are many queries might be doing a read. They're not trying to modify. Having them go one after another has a significant impact not only in the concurrency in the system, but also user perceived performance. But then, as I said, if you're actually making a modification to your table, then you need a lock. And you want to block all other readers or even other writers at the same time. Okay? So this class of problems is important. It's called a reader-writer problem. Okay? So essentially, you want to allow, in this case, multiple readers to read the data item concurrently, but you want to, once there's a writer, you want to block. Okay? So in other words, you want to still have a lock primitive, but you want to acquire the lock in two different modes. If you acquire the lock in read mode, you get a read lock. Okay? In this case, other threads can also acquire the lock in read mode. Okay? Which means more than one thread holds the lock, but in read mode only. But if you, on the other hand, acquire the lock in the write mode, everything else is blocked. Whether other threads try to get it in the read mode or a write mode, they will all have to block until the writer is done. Okay? So if the writer does get the right lock in write. So now you have generalized the notion of a lock to have multiple modes in which you acquire. You don't require, you say I want to get the lock in a read-only mode or a write mode. Okay. So now if you actually know anything about locks or libraries, you will see that there you get the notion of a read-write lock. Okay. Other than a simple lock, you can also get what is called a read-write lock, which will give you exactly this semantics. You can get the lock in read mode or write mode. But the problem we want to address here is how do we solve this problem? Okay? We know what semaphores are, we know what monitors are, we even know what standard lock is. Can we implement a read-write lock abstraction, a class, using any of these underlying methods, which will allow multiple readers but only one writer? Okay? Then if you use that, then you can implement other things on top of it that will take advantage of this problem. Okay? So this is essentially the reader-writer problem. I just wanted to introduce this problem and then we'll actually look at solutions to more of your question.
Yeah, would there ever be an example where you would have more than one writer accessing at a time? Like, just Google Drive comes to mind, where you have multiple people editing a document at that very second.
Yeah.
Is the implementation something where you would have multiple writers, or is it sort of buffering your input and then putting it in when it comes around?
So the two questions you asked, can you have multiple writers and does it make sense? Right? So the two slightly different questions. So if you have a synchronization problem where for correctness reasons you do not want more than one writer, okay? Then you want to actually have a lock and block other writers. Okay? Examples are you are trying to modify a linked list where you're mucking around with the next pointer and so on. If two threads go in and try to do something, then they overwrite one another and then mess up the linkage, will have corrupt data structure. So there are many scenarios where you never want more than one writer. Okay? You may not even want readers, let alone other writers. Okay? Having said that, the example that you were mentioning, which is collaborative editing of a document, okay, is basically there is no lock there at all. Basically, they let people edit, and we are allowing humans to figure out whether things are conflicting. If you can see that somebody's red cursor is editing this sentence, if I go and try to overwrite the content, I know I'm doing something wrong, which is I did some other part of the document. So you can certainly have scenarios where you have collaborative writers with no locks at all. Okay? And they're assuming that conflicts can happen, but you're not using a lock to resolve the conflict, you're allowing users to figure out. If you write something, I go mess it up, then you get upset with me and you want to make me redo the one or something like this. So you'll have to use other mechanisms to ensure correctness. Locks won't do that. Okay. Right. So we'll stop here. For those of you who came late, there is a discussion section tomorrow, but it will be a regular lecture. It's a makeup lecture from a missed class in 2 weeks. Okay. So do come, not here, come to the discussion room, and we will have a lecture tomorrow.
Back.